as anything else. So again, for those who are away, you need to watch the video. You need to take the notes in order to understand what's happening. I did do something a little differently, though, this time. I saved the version of the PowerPoint that has my writing on it. So if you're just copying the notes, you want to copy that part. And so I saved it as something different. You'll notice it'll say charging by contact with notes, which means all of my little annotations and things are in the PowerPoint now. Okay. So remember, charging by contact means that we are going to be taking a conductive sphere or a conductive object, and we are going to touch it to a charged object to force electron transfer, right? And remember, it's the electrons that are moving. So we talked about induced charge separation. I don't want to talk that much about that right now. Let's talk about charging by conduction. So at this point, we talked about how we could take an object that was neutral, all right, 4 positives and 4 negatives, bring it into contact with an object that is negative, and cause that charge to transfer to it, okay? And the reason it transfers, well, why do you think all of the negatives on here want to go to the neutral object? All right? And when I say want, I don't mean that they've got little desires. Gee whiz, I wish I was on that neutral object. Electrons don't have little brains, so they don't make conscious decisions. Even though I'm saying the word want, I want you to explain in terms of attraction and repulsion why it would do such a thing. Yes, Jess? That's a true statement. The negatives would want to be near the positives. Correct. Why else? There's a second reason. That's a good reason, though. Yep. So those negatives on the negative objects are repelling each other. If they can get further away from each other, that's a good thing. So they're literally repelled off of one and also attracted to those positives. Yes. Now, you are getting into some very fine points of the way this works, all right? And you're right, there will be a size effect. There will also be a curvature effect. If I've got a really small object, it'll be different than if the object's large, okay? We're going to just pretend that those don't exist right now because the mathematics for that type of explanation gets really tough. And that's a grade 12 university level physics problem that we do solve, right? That type of thing. But you're right, there would be some of those effects. But we're not going to worry about that here. Okay, awesome. So they're going to want to repel away. And then we did some counting where we noticed that we had 8, or was it 2, 4, 6, 8, 10. We had 10 of these negatives to make a negative 6. We had equal numbers of negatives and positives to make 0. And then we transferred them so that they would become equal, all right? Because they will repel to become equal. But let's imagine that we actually couldn't see the number of electrons on there. Let's say we couldn't see any of that information. Because in a real ball, there's not just 4 nucleuses, there's billions and billions and billions and billions and billions and billions of them, right? We get the idea? So we can do this without actually counting the electrons and just starting with the charges. So let's ignore the electrons and just think about the charge. On the neutral one, we have 0. On the negative one, we have negative 6. And in the end, we came up with an answer of negative 3 each. How do you think we could explain that if we didn't even think about the electrons? What could we do mathematically that would get us from this information down to here? What do you think? What do you think? Yeah, what do you think, Travis? Divide what by 2? So the negative 6, spread it out over the 2, and therefore divide it by 2. That's correct. I could touch 3 objects together and make all 3 objects become contacted, What would the charge be on each of the objects if I had 3 objects contacted together? How did you get that? Because it would spread over the 3. Excellent, good. So the way that I would do this, and I'm not going to make you do a problem that has 3 of them, but that's the way it would work. The charges would spread out. So to do this, if we knew nothing about this in here, I would start with the overall charge, 0 plus -6 gives me a total charge of -6, right? So I'm adding the 2 charges together. And now because there's 2 objects, it's going to be the -6 divided by 2, which gives me -3 each. Okay? So add the 2 charges together to get an overall charge, and then divide that charge by how many things are touching. In this case, there's just 2. All right? Yep?
On the top one.
Yep.
The one that you start out with.
Yep.
Negative.
It's 0, actually. Oh, this guy.
Yeah.
Negative, correct.
It starts out as negative.
Yes.
And then you, you
Touch it.
touch them.
Yep.
And then that one becomes negative, but the other one becomes neutral.
This one here.
Like,
This guy here.
yeah, so that, on the top side there,
Yep.
there's the negative one, and then there's the neutral one. And then when they transfer over, the neutral one becomes negative. And does the other one stay negative, or does it become neutral?
It will stay negative because while they're in contact, the electrons aren't going to all jump onto the neutral one. They'll spread themselves out over both. Why wouldn't all the electrons jump onto the neutral one? There's a reason for it. Why wouldn't all the electrons pile up? You're going to answer your own question. This is awesome, Jess.
Is it because of the 4, like the 4 positives that are left on that one?
That's going to hold some back. That's a good way of thinking of it. Why else wouldn't they all pile up? Yep. Not that they want to make both of them neutral. No. Yep.
Because then they would still be all together.
They would still be all together, and they're going to repel to spread each other out. Right? So both answers are correct. They'll be attracted to those, back to those, and they'll spread each other out because they always spread out. Let's take a look at some of the other ones that we did. Taking a look at the next one. So, without looking at any of these charges, what's the total charge? What's the total charge on my 2 objects? What's the total charge? Yeah, go ahead. It's +2. 0 plus +2 is +2. It's going to be spread over 2 objects. What's the charge going to be on each? Yep, Danton? Because I'm going to divide that by 2. +2 divided by 2 equals +1 on each. That math will get it correct every time. We need that total charge, and then we need to separate it over the 2. And here we had one that was positive and negative, and let's see if the math works. What was the first thing I had to do here? What do I have to get first? Yeah, the total charge. I have a +2 plus a -4. What's the total charge after the positives and the negatives cancel each other out? What's that total charge going to be, Jack? It's going to be -2, and now I'm going to distribute it over 2 objects, -2 divided by 2, and see that we get -1 as the charge. All right? So that works, yep. Now, we're talking about single electrons, right? But remember, in an actual object, there's billions and billions and billions and billions of them, okay? So, in physics, we actually don't count individual electrons. We can't do it. They're too small. So we've created units that put electrons into big groupings. Just like if we were to, say, sell cobs of corn, we sell them in dozens instead of individual cobs of corn, okay? Now, a dozen is a small number. But in electricity, we put charges into groups called coulombs. and there's a large number of electrons in coulombs. And the number, and I don't remember it exactly, but I think it's approximately 10 to the 19 electrons in 1 coulomb. So instead of me talking about just these numbers, it would make more sense for me to say that there's +2 coulombs, capital C, on the left one, -4 coulombs on the right one, and then if we end up with a half, it's okay, because it's like a half a dozen, okay? So we don't actually ever count individual electrons, they're too small. I'm just doing it this way to introduce you kind of the way that we talk about it. So it would be okay to get fractions, because in reality, we put them in these really big groups, okay? All right? Okay, I'm gonna stop this little video for a second, and then I'm gonna take up the work. So let's get our homework out at this point, and now we can explain some of the stuff that we're gonna have to talk about in the homework.